do you? Okay, you can record now. Okay, no problem. So basically, the idea is, first thing is, why do we need this thing, right? It's called NHST, null hypothesis significance testing, right? First thing is, why do you need it, right? So what happens is, in a lot of cases, what will happen is you have two populations, let's say A and B, and there will be some properties of each population. And first thing we should understand is what is null distribution and what is null hypothesis. And we'll look at the code also, and we will not do any complicated formulas today, not even statistics, just one formula. Otherwise, so what is null hypothesis? So null hypothesis is simply the statement that these two populations are equivalent. This population A, this population B, these are equivalent. So this is called a null hypothesis. And there can be many ways to say that these are the same or not. One option is, let's say this is a population of numbers. Let's say you are doing revenue measurement of two populations. So obviously you can have the mean revenue of population A, the mean revenue of population B, right? Now the question is, let's say you have some product and you launch a new feature, and that new feature will impact your revenue of the product, right? May or may not. So let's say earlier the revenue was 100 rupees. Now after launching the new feature into the product, the revenue became 105 rupees, right? Now you'll say that, okay, my increment in revenue is 105 minus 100, right? Which is basically 5 rupees. Let's call it delta or something. Now the question is this 5 rupees a big enough number to be sure that this thing didn't happen because of chance, right? Because whenever you make any change in the system, there will be some variation in numbers. It could be because of randomness, it could be because it's a new day, it rained, whatever, right? So how do we know that this positive result we got, which is 5 rupees increment in revenue, is actually not by chance? That is the goal. Any questions here? Okay. Okay. So what we'll do next is understand what is a null distribution. Forget about that. So what we'll do is, like, we have these two population A and B. We do a random shuffle. Obviously, then this population will be mixed with this, and every time you shuffle, they are exchanging items in the set, right? So you do a random shuffle, and then you try to find the new mean and the new mean here. And because you have shuffled, hopefully the two populations are similar now, right? But still it will have some difference, right? Let's say this time when I shuffle it, let's say shuffle number 1. In shuffle number 1, maybe the second population is now 104 and the first population is, let's say, 101. Still I'm getting 4 rupees extra because of the shuffling. I shuffle it again, and let's say this time my population is, I don't know, let's say 103 rupees. And the population B, let's say because of the shuffling, became 101 rupees. Now the revenue went down by this shuffle, right? Which is minus 2 rupees. So at least you can understand that this shuffling is actually introducing a structure here where the two population now should become equivalent because I'm shuffling. Does this make sense?
Yeah.
Right? This is super simple. So now what we do is, let's say I will do this shuffling 10,000 times. And every time I shuffle, I'll get this delta. Sometimes the revenue is positive, +4. Sometimes it is +10. Sometimes it's -4. We'll get a lot of numbers whenever we do this shuffle, right? And with these numbers, what I can do is plot a histogram or some distribution with these numbers, right? And let's say the mean number for this distribution is, I don't know, +5 or whatever. But the point is, because of this shuffling, I'm getting a lot of deltas. And even when the populations are hopefully the same, still I'm getting these kind of variations. Does this make sense? Now, the thing is, the population are the same. Still I'm getting the variation. And this plot which I plotted is called null distribution. Which really means is that the two populations are the same. Just because of randomness, just by chance, I'm getting some kind of variation in the effect. Does this make sense?
Yes.
Sorry, so I just joined a bit late. I had to call got cut. So these are technically different populations, right? So
Yes.
we are saying that they are same because of the null hypothesis, or we know that it's same.
No. So we don't know if they are same or not, right? We may have to. So the end goal is to find whether one population is better than the other. That is the goal, to find out. But because I'm shuffling between the population, in the shuffling case, these two populations should be the same.
Okay, sorry. Can you just repeat that shuffle case alone?
So suppose
So
set A has 5,000, set B has 5,200. Will you take equal number from A, put it to B, and keep equal number from B and put it into A without overlap? I think that clarity is important.
For more clarity, I'll just paste some code here. Basically, I have two population, x1 and x2, let's say equal size. I'm just shuffling them. I concatenate them and then shuffle, break it down again. That's it. So basically what I'm just trying to do is shuffle. I mix it up, shuffle, break it down again. And because of this shuffling, this population is obviously the same.
Okay.
Right? If someone wants to look at the code, I'll just wait for 20 seconds. I'll just explain the code. I have two population, x1 and x2, which is the list of revenues for the two population. Right now, let's assume it's equal population. I just concatenate the two population and then permute, which is shuffle, break it down again, which is basically mix all the numbers in a bag, shuffle it, bring it back into two bags again. Right?
So the interesting thing is n1 equal to len of x1 ensures that the population count of each of the sets remains the same after the shuffling.
Yes, but let's not go there. Let's, for simplicity, keep it equal, right? Because then we could say other things. There will be other questions. I don't want to get there. But at the least, if I shuffle, there should be no doubt that in equal population, this shuffling will create two populations, which every time I shuffle, potentially is the same population in statistics. This should make sense, right? Now, every time I shuffle and I find the mean of the two population, even if the two populations are the same, I will get variations around the difference in the mean, right? And that is called a null distribution, which is saying that when the population are the same, if I plot the histogram of the differences, it will have a distribution. There will be some randomness because of this shuffling. I'll come to it why we want to learn this, but at least this should be clear. Any questions? Okay. So now the name is null hypothesis significant testing, right? Now we know what is a null hypothesis. Now, what happens in NHST is whatever we do is under the null hypothesis, which means that everything we do assumes that the two population is similar and assumes that we know that distribution, and conditioned on this distribution, we go further, right? Now, what I want to do is, this is a distribution if the population was equal. Now, let's say I observe something, which is my old population A and B, which is actually different, right? We have not shuffled them. I'll calculate the mean here and here. Let's say this one is 100, this one is 105. So the difference is 5 rupees, right? If I plot it here, let's say mean is around 0, whatever, or maybe mean is around 1. 5 rupees comes somewhere here, right? So the question is this 5 rupee increment in the revenue, right? In these two population, is this 5 rupee increment I'm getting here, is this because of randomness, or is because it's truly better than the other, right? It is not because of randomness, right? Now, what will happen is, around this peak, if you're very close to these places around this peak, it is highly likely that the increment you are getting here, let's say 5 rupees was here, right? When 5 rupees was here, it is very likely that this 5 rupees could have been there for me just because of randomness. So the chances of me trusting this number 5 is very, very low, right? Versus if it is very far away in this corner, then I would say that, okay, the chances of me seeing this 5 rupees by random because of shuffling is very, very low, right? And what is p-value? In this distribution, if I try to find how many numbers of this histogram or this list I've collected by shuffling, how many of them are falling here, right? And if this number is pretty small, let's say 0.05, let's say only 5% of this random numbers are sampled by shuffling. If that number is so small, it's less than 5%, I'll say that I'm pretty confident that this mean difference of 5 which I've seen is actually not by luck. It is actually pretty extreme case. Does this make sense? This is the place where I might write a formula, simple formula A by B or something like that. But whatever I explained should be very simple and clear.
So,
any questions here?
Yes, an interpretation question. Suppose in B, say a handful of 5 or 6 people got increment of or revenue was significantly higher, like 130, 150, 160, and the others were pretty much flat, and hence they contributed towards that 5%. Versus a case where in B everybody rose or majority rose significantly, and hence contributed to the 5%, the increase of 5. In which case, which of the two cases that I mentioned will the null hypothesis be rejected? That is, you get a line, that 5 line is towards the tail, versus in which case would it be towards the mean?
See, whatever I've said is absolutely true. It is just that number of shuffling you will have to do is very, very large. Like instead of 10,000, maybe you need 100 million. The number is not important, but for a high enough number of shufflings, this statement remains true that you'll have 10 million of these differences when you shuffle. You get a distribution, and if the number you have actually seen in real observation is again 5 rupees, let's say, where is 5 rupees lying, right? If that 5 rupees is so extreme that only 5% of the population is above this 5 rupee, then it is actually pretty extreme, and it doesn't matter how it formed, right?
So you're looking at a macro level where is it significant or not based on shuffling. Okay.
I'm just trying to explain what is the meaning of statistical significance.
Yeah, but there is no interpretation we can do based on what I said, right? Like, I mean, you may have one or two Ambani Adanis who skew the thing, and when you shuffle, that Ambani Adani may not go to the A side, even if you do it 100 million times, with a population of 1.4
No, it
billion.
will. It might get rejected because when you shuffle, there's a very small number. Let's say 2 people, right? And let's say there are 1 lakh samples in each. What are the chances that these two will go here and here, right?
Very small, yeah.
So because of that, actually, the chance of your number going on this side, basically, it will work out. What I'm trying to say.
Got it.
So this is the intuition of what we are trying to achieve. Any question, any dumb question, any kind of question is good enough question. Unmute. Very small number of people. I don't read the chats. Null distribution is, someone has written something. Null distribution refers to a distribution of null hypothesis. Correct. That is what we have explained by shuffling, right?
Hey, hi. So generally, we learn in any resources. So this explanation they give is they take a sample out of it, and then the 10,000 different samples or 100,000 different samples are taken, and then this is calculated, right? Is that a bit different from your shuffling intuition you're trying to give?
See, what we are trying to do here is to understand what is the meaning of p-value, because a lot of interview questions will be like, they'll say something and they will hope that you'll say that this is the wrong statement. Like day before yesterday, I had a rapid fire ML round at a company where they quickly ask you questions again and again. In 2 minutes, you have to answer something. Next question, right? Now, a lot of times, one of the ways to say what is the p-value is, whatever difference you have observed, the random variable you are looking at under the null hypothesis, which is all these TIs, right? Let's say these numbers, each of these numbers are TI, which is because of shuffling. Now, what is the p-value? P-value is basically probability, and my observed delta is here 5 rupees, right? So p-value is basically the probability that my TI is basically my TI is less than equal to my delta, which is 5 rupees here, given my null hypothesis is true, right? This is the first formula and the last formula I will ever write. And I'll just say that this is, let's say, B by H or something, whatever, right? I'll tell you what it is eventually. But this is a complicated formula to see what is really a p-value, right? And a lot of times we don't understand. Like people will say that, okay, whatever you observed under null hypothesis, that observation is at least as extreme as the observed one, whatever, right? Some complicated thing. Now, how do you even decode this formula, right? How do you decode is, first you get a null distribution by shuffling, assuming that it is the same because you are shuffling. From that, you sample a lot of TIs and you do counting. How many of these TIs is actually less than your observed delta? You do counting. Let's say B of them were actually in this region, right? So anyways, so the point is, oh sorry, the other way around. It is extreme. I confused you. So what I'm trying to say is that this shaded area is related to this formula, which is actually a super complicated thing, which we totally see it in the wrong way. The right way to look at it is how we explained it. If you don't know this explanation, like it will be super complicated, and this under the null hypothesis is actually super important. If you don't say this in the interview, it is basically a wrong answer. You are rejected, right? Especially in analyst role and data science roles. So how do you remember this intuition for many years? Not by some complicated formula, right? So you remember it in a simple way. First, you have to understand what is a null hypothesis, because you are conditioning everything in null hypothesis. How do you get that? You can shuffle the population and again. See, eventually we'll use formula, like under T distribution, whatever. That is fine. But how do you remember and understand something? So you take two population, you shuffle it again and again, 100 million times, whatever. You get 100 million data points, which is the subtraction of the mean of these two, which will give you some histogram. You can plot the histogram, see it, whatever. Now, under this null distribution, these are the deltas. And there's one observed delta, which is a vertical line here. Now, where does this vertical line lie in this null distribution? Tells you that what you have observed, what increment you have seen, is either because of randomness or it's truly an increment. That is what we are solving for. And this complicated probability formula needs to be decoded, and that's what I'm trying to do.
So,
any questions here?
Yeah, before you go to the formula.
There's no formula.
Okay.
Okay. I'll just run this code and show you that I compute p-value.
Yeah. So the question is, do you reject the null hypothesis? The null hypothesis is that the two distributions are not different, and some small change is only by chance, and hence, if the 5 lies more than 2 standard deviations, assuming it's a Gaussian distribution or whatever the T distribution equivalent formula is, if it lies in the tail, then you reject the null hypothesis that they are not the same. Statistically speaking, they are not the same. Is that correct?
That is correct. I'm just trying to explain this formula. In the end, what we will do in the code is we shuffle, let's say 10,000 times or whatever. That becomes my denominator, 10,000. I have already observed my delta, let's say 5 rupees. I just do the counting that how many of them are above 5 rupees. I don't know, let's say 500 people, 500 items. This is my p-value, right? And just by counting, I have computed my p-value, and if this p-value is less than 0.05, let's say, or 0.01, depending on the standards you are following, I can say that, okay, this value I have observed is so extreme that it cannot happen by random. See, this is about interpretation and understanding. I know that there are formulas, there are t-tests and all that stuff. This is called, what I'm explaining here is called a permutation test. Okay? If people want to know the name of what it is. T-test is a different kind of a test, and that is what we will use. It's efficient. It assumes that this delta, this null hypothesis follows the T distribution, right? That is fine. There are other distributions. You can follow whatever. But what I'm trying to explain is just this probability and how to really understand what is a p-value under null hypothesis. So whenever someone says that this delta is distributed according to student T or whatever, what it really means is, assuming the two populations are the same, if I randomly shuffle, what is the distribution it will follow? That is my null distribution. Any questions here?
Yeah, one question. I think this is a silly question. So how are we calculating delta? I understand we are shuffling, we are getting 10,000 numbers, the difference in means. So we have created this distribution altogether, right? So the specific delta equal to 5, is it one of the sample difference? Is that the case? That's the first question. Yeah. Second one is the intuition that we are trying to get, right? So if it is extreme, we are saying that the probability of that happening by a chance is very less. So it's an extreme case. So there is some issue here. We are rejecting the null hypothesis. That's how the logic dictates. So the question in itself is, how are we saying that? Like, because it's extreme, what is making us to say that it can't come by chance, happen by chance?
You exactly know that exactly 5% of population can only happen beyond this number, right? Because of randomness in the data, if it was the same, right? So if you know that only 5% population can exceed this number, Because you are basically saying that this is a pretty extreme value.
That's my question. It's sort of counterintuitive, right? Only 5% of the numbers are crossing that.
See, I'm not saying that it cannot happen by randomness. I'm just saying that when the two populations were same, when I shuffle and I see the variation, there is a certain variation which can happen if I take all the possibilities of shuffling, and that variation will give me a natural variance of that delta I'm observing, right? Now, I know the natural variation. Even after knowing that if it is pretty extreme, then it is unlikely event, right? There's no guarantee ever in probability.
Okay, got it.
So, see, I've written some code here. So what we are doing here is just counting. So p-value we have already explained that the probability that basically the null distribution TI is at least as extreme as the computed difference in population, which is the five rupees. Given that my null hypothesis is true, and I'm just saying that I'll count it, I'll do the B by M. +1 is because of some numerical stability, let's say, right? So, so what we do is we write a shuffle function. We just shuffle, basically concatenate, shuffle, and break it down again.
Yeah, just pause now, here. Just pause there. So every time in your 10,000 or 1 million tests or 10 million tests, you're not taking the same amount of random samples from B and keeping it aside, and same number of random.
No, data is fixed.
Data is fixed. Data is fixed. But if imagine A and B were two bags, okay, you're not taking out n number, say 50 from B, keeping it aside, 50 from A, keeping it aside, and then swapping it. You're not.
No, it is fixed. If it is, look at the shaded code. It is fixed.
How can that be fixed? Because if you are shuffling permutation NP concatenate, so you're concatenating x1 and x2, and then you're permuting it, so it's a random shuffle, right? And then you're going 0 to n1.
No, but x1, size of x1 and size of the first returned value is the same.
No, size is the same. A and B will still let's say A has 500 balls, B has 550 balls. Okay, I'm taking 25 aside from B, keeping it on my right hand, 25 aside from A, keeping it on my left hand. Okay, then taking the B, taking my right hand, the balls in my right hand, putting it into A, taking the balls in the left hand, putting it to B. Now, the count remains the same, but the 25 is not the same in this every time.
Obviously. That's shuffling, right?
Yes, that's complete shuffling. Okay. So that's an important thing to note in the experiment creation.
Yeah. Obviously, shuffling is there, and every time we get two bags, highly likely they are totally different bags, right? In some sense. So this is a shuffle function, super simple. For this experiment, at least I just have a small number of permutations. Now I have generated some fake data. First data is some normal distribution, 200 samples. Second population is also some normal distribution, but I've added 0.5 to it. So there's a difference of 0.5 on average in these two populations. Okay. So the true difference between these two is 0.5 actually. I've synthetically generated it, but in a real world scenario, you'll have two populations. We'll find the mean of these two populations, we'll get something. We'll also find the difference of these two populations directly. This is my delta $5 revenue, which I was talking about, right? This is my observed delta. I'll fix it. It will be fixed throughout the experiment. This has been my observation. This is what I've observed in my experiment. Now, what I'll do is I'll shuffle this again and again 5,000 times, right? And then I will collect all the differences which I can see while shuffling. These means are my null distribution means. And I'll just do my counting, which is this way. Receive this B plus 1 by M plus 1. M is my 5,000. B is just I'll count that how many of my observations under null distribution is more extreme than my observed. This is my p-value by definition. Okay. Now my p-value here is 0.0001. So actually these two populations are different. Okay. So this is a simple experiment which really explains you what it is. Now in real world, these kind of methods can be super data hungry. These methods should only be used when you don't know the distribution of your delta, or you don't want to go that way. This method doesn't assume any kind of distribution of my p-value, this p, right? It is counting. So it's a very powerful method. It's called permutation method, but it also reveals what this really is, right? Any questions here?
Yeah, I'm trying to associate it with.
See, don't build a wall around you with your old knowledge, right? This was the formula I had seen before.
Just engage me a little bit here. Just engage me. The simplest example of p-value that I have ever taught and is with.
This is the simplest, I think.
Well, hold on. The simplest one I've ever taught is a coin biased or not, right?
Same thing, yeah.
Okay, so you have heads and tails in a coin. You toss it 100 times, and you get 62 heads. Next time again you toss it 100 times and you get 58 heads, and so on and so forth, right? Now, if you had to make an analogy between this permutation, the shuffling and permutation with the coins, I'm guessing that if it was indeed a biased coin, your shuffling method would have also caught a biased coin as this exact simulation would have also caught the p-value. It would have been beyond the p-value, and hence we would have rejected the null hypothesis that the coin is unbiased. So it's a nice experiment that we can try to make it. There is no two bags here. Maybe we can take number of heads and number of tails, and then one bag is.
By the way, I'm showing you this code on a browser.
Yeah. So
no, I cannot run it. It's on browser.
No, that's fine. I'm just saying that it can be simulated. Even the coin toss simplest example can be simulated using exactly this method.
I totally agree with you.
Where
we should simulate and it will work out with high number of enough of samples, because this method doesn't assume any kind of distribution. It will work, right? So I don't see any problem with that. You simulate it and it will work. It's not a problem. The only thing I'm trying to say is that usually with other methods, we assume some distribution of this thing. That is the only difference. Otherwise, there's no difference. But I'm just trying to explain what those distributions really mean internally.
Got it.
Because a lot of times we think that this is not conditioned on null hypothesis. It is just a distribution of deltas in the observed space. It's not true, right? That is what I want to try to emphasize. That this conditioning on null distribution is super important, and it is in the name of the method itself, NHST, null hypothesis significance testing, right? It's in the name. So this conditioning on null hypothesis and this shuffling idea or assumption that if the two populations were equal, what would be the difference distribution? And on that distribution, we do whatever we do. That is the most important thing I want to emphasize today. Not relevant to exact methods, whatever, right?
Can you just say how did you get the p-value? How was the p-value computed? It is
b plus 1 by n plus 1. And I'm just counting here, right?
Yeah, no.
I just count that whether my observed delta under my null hypothesis, how many of them are more extreme than the true observed difference, divided by the total number of permutations, right?
Yeah. So instead of that 0.5, x2 is equal to npr dot normal size, if you had put a random, if you had made a Gaussian distribution with mean of 0.5, your p-value would have been bigger than the observed the p-value that you got, but it would still be less than 0.05. It's worth maybe trying.
Yeah, sure. So I'm just saying that it will work out.
Yeah.
Whatever you are saying, it will work out.
Yeah.
In fact, if you have a bigger number, p-value will become even more smaller. I feel.
Yeah, I'm saying that
Because,
if the 0.5 is replaced with distribution, a Gaussian distribution with 0.5 and maybe standard deviation of 0.5, we make it like a Poisson distribution. Even then, I think you would see a p-value that would be less than 0.05. It may not be as low as what you got because you are consistently 0.5 more in the x2 case.
Yeah. So this method has certain disadvantages, that statistical power is pretty low. So you need a lot of samples and things like that. But this method is preferred when you have no analytical form of the solution. Like basically, you don't want to assume anything. So this is the most general form of it. It will work always with large enough data. So yeah, it would be interesting to change these values, play around with it, change these distributions. I get it, but it will work out. What else? But anyways, hopefully conceptually everyone understands without getting into formulas what really is we mean by null hypothesis significant testing, right? And one more thing, we assumed 0.05 or 0.01. These are the standard numbers. If your p-value is below that number, you say that the difference is statistically significant, and we have a lot of confidence in the repeatability of the experiment, that whatever number of times you do the experiment, you will get the same conclusion that it is significant, right? So at least this part hopefully should be clear. Anyone feels that it's super complicated? It should be simple.
So I'll just paraphrase, and
I'll just wait for other people to ask, then we can continue.
Yeah.
Anyone else has any questions? Then we will continue with Vijay. I just don't want anyone to be confused with simple things. And there's no bad questions here, by the way. Yeah. Okay, fine. Okay, Vijay, continue.
Yeah.
I don't think anyone else has it. Yeah.
So the paraphrasing is that the null hypothesis assumes that the two distributions are the same.
No. Null hypothesis and null distribution assumes that.
Null distribution.
Yeah, null hypothesis also assumes that the two populations are the same.
Similar.
But different variations of the same population. Yeah.
Right. And when you get a p-value that is either on the right tail or the left tail, depending on the problem that you're solving. So in this case, you picked, so if your p-value was say 0.97, and it was a two-tail test, then you would again say that this is highly unlikely to happen. So I guess if you are...
basically your condition will only change, right? That the true difference plus minus, basically this time we are computing only the right hand side. In this condition you make a change that we measure on the both extremes.
Right.
So still the same, right? Counting. So
right.
Yeah, two tail, one tail, whatever you want to do is fine. It depends on the situation and the problem. But in the end, it's counting of ratios. I just want to super simplify it.
If your p-value was 0.97, I don't think you would have to change the formula. I think the code as is would be the same. If your p-value was 0.97, even then you would reject the null hypothesis. So if you change your 0.5 plus 0.5 to the x1 instead and remove it from x2, then you would get a point, I'm guessing you would get a 0.998 81 as your p-value. It would be the opposite of...
No, it will be extreme only. I don't know why you are saying that.
The point, okay.
Oh, in that sense, you're saying that the sign has changed. It's negative.
Yeah. It's worth playing with it. I mean, it'll get a better intuition. You should share the code.
If the revenue of the new feature is lower than the observed old feature, you won't even do a test. Right? There's no signal, it's lower. If it's higher, then we are not sure that whether it's by randomness or...
So but lower also whether it negatively impacted the campaign, say for example, or negatively impacted something. So an extremity can be on either the left side or the right side. So I think it would be, anyways, I'll play. Send me the code, I'll play.
Then you have to rewrite your condition that you are calculating the left hand side.
What makes it left hand side over here?
Less than equal to, greater than equal to. So right now it's $5, let's say, and I'm saying that whether my null distribution extremes, how many of them are more than $5, right?
Okay.
If it is a minus $5, I'll say that how many of them is less than minus $5 because we will want to compute the negative impact.
So I'm just then thinking B plus 1 over M plus 1, the formula, it's not...
That will always be the same.
It's not cumulative.
No, it depends on you, na? What is the meaning of extreme? Because I'm just saying Ti is at least as extreme as what you observe. Now the meaning of extreme is defined by you. You can take one tail, two tail, left tail, right tail. It's all your choice, right? This highlighted formula, right? This plot. So definition of p-value is this Ti is at least as extreme as observed. Now what is the meaning of extreme is up to us. And at least in a one-sided tail, right tail, even the code is aligning with that. If you want a two-tailed, you need a condition where you see that tail ka volume plus that tail ka volume, you add those volumes, your B is basically a bigger number, right? And that is also fine. You have to define what is extreme. I mean, I am trying to simplify, but I feel like we are trying to complicate.
Right? I'm trying to get into the weeds of it.
Yeah.
That's all.
No, I get it. But I'm just saying that this is the most granular form of understanding this statement, what is p-value, right? Because probability is counting at the core. Beta, whatever you have learned after that, like counting is the most core of what is a probability. And that's how we learn probability, by counting initially, right?
Yeah.
So I feel like this is the most basic version of this thing. By the way, others also feel free to ask questions. There's no dumb questions. Yeah. Okay, cool. What else? So yeah, I mean, that's what I wanted to share today because I wanted to super simplify things. Of course, there is like complicated ways to do things like there are some formulas, Z test, T test, when you use what, and you assume some distributions, and it will do the same thing but with a complicated formula. You can see here with my mouse, right? So it will do the same thing with some complicated formula. Otherwise, intuition is always the same, right? I just want today's takeaway is the theory is super simple. Just to be data efficient, we assume certain things and we get closed form solutions and we do super simple. You can unmute, it's a super small group. Someone wrote something. The chat. Resources. Okay. I mean, there are too many resources for hypothesis testing and it can be from super simple to super complicated. One